Given an arbitrary function, my goal is to estimate the derivative at various points. I started with the obvious approach. I described this in a previous video. It gives good results, usually good enough. But I'm practicing for sum 4, so good enough won't do. Here's the problem. Ideally, we can get our 2 points as close to each other as we want, so we can get as good an estimate as we want. But in the real world, you run into precision issues if the 2 points get too close together. How do you know if the points are too close? Most of the time you can make a reasonable guess, then you just try it. That works as long as you're not pushing any limits. And with almost 16 digits of precision coming standard, you almost never push the limits. If you take this algorithm as is and just try to push it to the limit, you'll find the limit is fuzzy and difficult to compute. If you really want to push the limits, you need a better approach. Let me show you a simple way to get a highly accurate estimate of a derivative. Less brute force math, more smarter math. My solution was so simple, I was surprised that it worked as well as it did. I mean, it should have worked, of course, but I just got so much out of this simple thing, I had to know more. Okay, let's take a closer look, especially if you're not a programmer. All I did, I took a sample at one point, at the closest point that I felt comfortable, and then I took a sample at a second point that was twice as far away, and I wanted to know what the answer would be at 0, at this 0 divided by 0, this magic point. So all I did was extrapolate, just a straight line, just the simplest way to improve on this already simple solution. So, why does this work so well? Short version, we were using an estimate that was only linear, and now we're using an estimate that is quadratic. Crudely speaking, imagine a Taylor expansion saying what we really need and how many terms do we keep. We were keeping 2, and now we're keeping 3. You could do the algebra, but if you look, the important thing is there. We've added another power of x. How much does this matter? It depends how close your points are together. In calculus class, you assume you can get these points just as close together as you want. At that point, you know that you can ignore anything except for dx. Anything like dx squared immediately goes away. I'm jumping around a bit. I'm showing several different perspectives of the same thing. Please don't get distracted by the details. Here, for example, I'm dividing by dx, so dx to the second power, dx squared on that line, does not mean the same thing as dx squared here. The important thing is my new improved formula moves an entire power in the happy direction. When I say linear, I'm really talking about this equation, in particular this error here. The error is proportional to dx. It's linearly proportional. So that means if I can make dx 10 times smaller, my error will be 10 times smaller. Here, this is why I keep saying quadratic for the new and improved thing. Notice that we are squaring dx. That means if I can make dx 10 times smaller, I can make my error 100 times smaller. This allows me to find a sweet spot for dx. Now I can make the error in my formula too small to notice without making dx too small to calculate with. You've probably seen this drawing before. This shows the difference between the initial function, the derivative, and the different components of the derivative. Normally we only look at the first level, just at dx. We say dx squared and dx cubed and all the rest are just too small to care about. But in the real world, helps to go just a little bit further. Now I'm saying that we can't throw away this squared term. However, we're still just making an estimate. We're still going to throw away a lot of terms, but it's good enough. Is it really good enough? Is there something about quadratics that really is just that much better than a linear equation? Well, I hope so. My goal with all this is actually some graphics stuff, and I'm using all of this just to make better quadratic equations, just to make these nice curves, these little Q commands that estimate any curve I want. Here's a circle, for example, and let's try 4 or 5 or 6 or 8 lines versus the same number of quadratics. Yeah, these are all just parabola segments, and that circle looks amazing, but the other circle, not quite so. The whole point of the Q command is that you don't need to describe every bit of your curve. You can estimate things really well with small quadratics. Thanks for watching. Links in the description below. Like, share, and subscribe.